हेलो दोस्तों, आपका स्वागत करता हूँ हमारे इस यूट्यूब चैनल में। प्लीज लाइक कीजिए और साथ ही साथ चैनल को
Moving at a
सब्सक्राइब
constant
कीजिए।
speed v, it's in uniform circular motion, at least as far as that goes. And what do we know about uniform circular motion? Well, we know that the car has to be accelerating that way, and its centripetal acceleration is equal to v squared over r. If it didn't have that acceleration, it wouldn't stay in the circle. So if its acceleration were less than that, what would happen is the car would be coming along, but if it was less than that, it's not going to turn enough and it'll skid out and go out here. If the acceleration were more, it'll turn in and go tighter than the circle. You just think about how the velocity would change. So it has to have that acceleration. To have that, it doesn't just have it. It's not, oh, it's moving in a circle, therefore there is centripetal acceleration. I mean, from a logic point of view, you can say, oh, I know there's centripetal acceleration because it's moving in a circle. But the moving in a circle doesn't give it that acceleration. There has to be a force to give it that acceleration. What is that force? Well, what I'm going to do is I'm going to look at the car from behind. So here's an eyeball. That's supposed to look like an eyeball. I'm going to look at the car from behind and draw a free body diagram. So this is looking at the back of the car. What are the forces on the car? Well, we have gravity down. We've got a normal force up, which really acts on all four tires. I'm going to draw it all on just one tire. We're going to abstract and just sum the whole thing together for one. Does it really matter? It does matter if you want to think about, if you think about cars going around turns. If you go too fast, among other things, the car could start to flip and roll. And to flip and roll, there would have to be a torque, and if that was the case, we would definitely want to think about the different force versus here to see if there's a net torque on the car. But we're not going to worry about that here. So what I'm going to do is just put all of the various four tires together, pretend they're all at one place, and for our purposes right now, we'll be okay. There's also, well, it's moving at a constant speed. So what that means is that there's no net force along the direction that it's moving. If there was a net force this way, it would be speeding up. If there was a net force that way, it would be slowing down. But it's moving at constant speed. So there's no net force along the direction it's moving. What that means is that if there is some air resistance, you'll have to have something that way, which will be static friction with the road. Let's leave air resistance out for now. But now remember, I'm looking at it from behind, so the car should be accelerating from the point of view of this guy. Imagine that you're there. That would be to the right. Did I do that right? Yes, to the right. So there has to be some force on the car to the right here. What is that force? And if you think about, all right, remember a force always rises from an interaction. The interaction is between what and what? Well, it could be the car and the air. That's not going to do it. That is how airplanes turn. They bank, and the wings push off of the air, and that's how they turn. That's how X-wings look like they turn in Star Wars, which is all wrong. But that's a story for another day. So what else is the car interacting with? You could say, well, the engine, but that would be a mistake too, because the engine's part of the car. Now, if it were a rocket car, and this is how X-wings really should turn, you could put a rocket on this side and fire gases out and cause the car to turn that way. But if you look outside of your car, I think you'll see there's no rocket engines sticking out. So the only other thing it's interacting with is the ground. So what is it that gives the force it needs to turn? It's static friction. So we're going to have a force of static friction between the wheel and the ground, and that's what gives the car the necessary force to turn. Well, okay, so then what's the first thing I want to do? The tighter the turn, the slower a car must go in order to complete the turn successfully. Okay, well, what does it mean to not complete the turn successfully? Let's just instinctively think about this. What happens if you come up to a curve and you're going too fast? What's going to happen? You're going to peel out and end up over here and probably crash into a telephone pole or something. Or maybe there's a big tank of like gas there and you crash into it and the whole thing explodes in a massive explosion. If you were in a movie, that's what would happen. So if you're peeling out here, that means that your acceleration wasn't enough. And if your acceleration wasn't enough to keep you in the turn, it means that the force wasn't enough. Now, static friction is the thing that we know about. Aha! Static friction, if you remember the equation we have for static friction, is this. Static friction has to be less than or equal to the coefficient of static friction times the normal force, where this is the normal force of interaction between the same two things that the static friction is between. So that's tire and road in this case for both of those forces. Okay, well, so the normal force, if you look vertically here, It's not, the car's not going up or down. So if you look vertically, we know that there's no net force because it's not accelerating. So Fn minus mg has to equal 0 in this case. So we know that the normal force in this case is just equal to mg. You're always tempted to substitute that in because in lots of problems it turns out to be that way. It's not. So the force of static friction has to be less than or equal to mu s mg. But also, we need the force of static friction to be equal to the mass of the car times the acceleration of the car, right? In order to stay in the turn, this is what the force has to be. And so we know that that's going to be mv squared over r, all right? So what I'm going to do is, we know that this is what static friction has to be. I'm going to substitute that back up there. mv squared over r has to be less than or equal to mu s times mg. I can divide m from both sides. Now the question is, the slower you have to go in order to complete the turn successfully, the tighter the turn. So let's just solve this for v and see what it says. V squared has to be less than mu s times g times r. So for a given coefficient of static friction, a given strength of gravity, which is what it is on Earth, the smaller r is, the smaller v has to be. Right? This tells you, take a square root of both sides, you will have the maximum speed that you can safely turn without losing the grip of your tires on the road and the car skidding out here and hitting that gas tank with the massive explosion we talked about earlier. Right, so this here explains that the smaller r is, in order to stay in the circle, the slower you have to go so that static friction is able to supply the necessary force. If you try to go faster, you are asking static friction to supply more force than it's capable of, and so therefore you won't actually have enough acceleration to stay in the circle and you'll go peeling out. So that's that first one. Now the second one, racetracks as well as freeway interchanges that curve are banked. All right, so what does that mean? Well, here's what I'm going to do. We're going to take this same picture here of a car turning. All right, and so we're going to look at it from the point of view of this guy here. So from the point of view of this guy, the car is going to the right. So imagine now, I'm going to start by drawing it, the road banked like this. This is what it means to be banked, is that the whole road kind of goes in and curves around and is banked like that. So we're looking to the right. The car is driving in. Oops, terrible car. The car is driving into the board, and as time goes by, it's going to go into the board and it's going to curve around that way. So that means is that because it's going in a uniform circular motion, it has to have some sort of centripetal acceleration that way in order to stay going. Well, let's go, or to stay in the circle, right? Let's draw a free body force diagram again. We have mg, but now the normal force is this way. And then finally there's going to be static friction. And I'll talk about that a little bit in a moment. But you see, here's the benefit of being banked this way, is that if you look at the normal force, it's no longer straight up, but it's at that angle. And so therefore, if you break the normal force down into components, right, you're going to have this is the component that has to balance vertically with the other forces, gravity, but then it turns out friction may have a bit too. This is the component that has to balance vertically so that the car doesn't jump off of the track. This is in the direction of AC. So therefore, this normal force can contribute to the centripetal force needed to keep the car moving in a circle. And so you don't have to ask as much of static friction. In fact, it turns out that if your speed is low enough, in fact, imagine the speed is 0, that's a pretty low speed, the forces I was drawing, the car will actually start sliding down. So if the force is low, if your speed is low enough, static friction will actually be that way to keep the car from sliding down the bank. So which direction is static friction? It depends entirely on how fast the car is going. The faster you go, the less this gets. There's going to be a perfect speed where there's no static friction and the normal force is just right, and the bank together is just right to keep the thing in a circle. And then as you go faster, though this component of the normal force isn't enough, you will need to have some friction that way in order to contribute to the centripetal force necessary to move the car in the circle. Now, it has to be banked in a specific direction. What if it was banked the other way, right? So suppose it was banked like this. And again, remember, this is a car that's going in and curving around that way. So the acceleration has to be that way. Well, now if I draw a free body force diagram, the normal force is that way, is opposite the acceleration. So now static friction has to be even bigger. It has to be big enough to supply the centripetal acceleration plus to offset the horizontal component of the normal force there. Right? Gravity is still just that way. So this is the way cars are banked. They're always banked into the curve. And if you go, next time you're driving on the freeway, you'll notice in these big interchanges that they are banked a little bit into the curve. Why do they do that? To help you make the turn. So that the car turning will be aided by the fact of the normal force on the road pushing up on the car. Also, if you watch car racing ever, like the Indianapolis 500 or whatever, you will notice that, especially for the really fast cars, there's a big, huge bank. In fact, even bike tracks and things like that have that. Finally, you have to drive slower to avoid losing control of your car on a curve when it's raining. So let's go back to what we had before. Let's just assume a flat road again. You're going around a curve. Right? So you have to have a centripetal acceleration that way because your car is going in and turning around that way. And remember, what we came up with was that it was static friction. Right? So there's mg and there's a normal force. Static friction had to equal mv squared over r, also has to be less than or equal to mu s times the normal force, or mu s times mg in this case. What that means is that, if again, when we solve this for v squared, what we had was mu s g r. When it's raining, the road gets more slick. This coefficient of friction will go down. You have less friction on a wet road. The tires are more likely to slide. So as this coefficient of friction goes down for a given r, the maximum safe speed goes down. So thinking about all of these things in terms of the rubber on the road being the thing, or the banked road with the normal force being the thing that gives the car the necessary centripetal force to go around a curve, it can answer all three of these questions. Now what's going to happen in the homework is I'm going to actually ask you to calculate some of this. But this tells you the kind of thinking that needs to go into it. And once you've got the free body diagrams, you can start trying to solve the right equations to figure out what you need. But this is how you get started with that kind of thing. So that is the first problem. Second problem. An amusement park roller coaster has a loop-to-loop section. The loop is 30 meters in diameter. How fast must a roller coaster be moving as it travels upside down over the top of the loop if the riders are not to fall out? So the basic idea is we have a roller coaster that's got a section in it like this. That's radius 30 meters. And then you have a car up here with a person in it standing on his head. A person sitting in the car. There's the legs and here's the head. Arms over the head saying, yeah! And the person has foolishly not buckled your seatbelt, because who does that in roller coasters? Now, if you just look at this, you think, well, okay, person falls out, splat on the ground. I guess I should get out the red pen, right? So here's the person, and that's it. End of person. That's what it looks like, right? It'll fall out if you don't have your seatbelt. But here's the thing. If the whole roller coaster is moving at speed v that way, or just including the person with it, well, this is a circle. So to stay in the circle, the person would have to have a centripetal acceleration AC equal to v squared over r to stay in the circle. So if this is the person's acceleration, then the person's going to stay in the circle and not fall out. That'll be pretty cool. Now the car is probably not going to fall off because it's probably got something gripping the rail. So the car is fine. It's just the person worried about. We don't want the blood streak down there because it's unsightly. So, how fast you have to be going for the person not to fall out. Well, let's just think about this. If you have the person down here, I'm just going to draw the person, free body diagram for the person, in the simplest case, where the person is basically just barely lifts off of the seat, the only force on the person is gravity. There's no forces in any other direction. Yeah, there's probably some air resistance, but we'll ignore that. It's going to be small, and it'll be offset by the seat pushing the person forward. Note that if the person is moving at a constant speed, v, there is no need to push the person that way to keep the person moving, unless there's air resistance to offset. The person will just continue going that way. So that's the force mg. Well, if the person's going to stay in a circle, then that is what's supplying the centripetal acceleration, that'll have to be equal to mv squared over r, right? This is just F equals ma. That's the force, that's ma. Or v squared has to equal gr, or you take the square root of both sides, v has to equal root gr. So that's exactly the speed you need to be going for gravity to exactly supply the centripetal force necessary to stay in the circle. Now here's the question. Let's think about, is this a maximum or a minimum speed? Well, if the car's moving slower, if v goes down, then the centripetal acceleration needed goes down. So v squared over r goes down, but gravity is not going to go down. So that means the force is more than is necessary to stay into a circle. And if the force is more than is necessary to stay into the circle, the person's going to accelerate out. That's when the person will fall out of the car. What if v squared is higher? Well, so if v is higher, if the thing is going faster, now this is more than this. And that's a problem because this is all the more force we have. But let's think about it. What happens if you've ever actually ridden one of these roller coasters? They go quite a bit faster than they need to. You actually feel yourself pressed into your seat. What's really happening is, so you're being pressed into your seat. The pressing you feel is the seat pushing back up on you. So you have a normal force that way, which is the seat pushing up on you. And in this case, mg plus the normal force of the seat pushing up on you, that together is what supplies your acceleration. Right? So now this is what F equals ma is, all in the downward direction. So now we think, okay, so what is the speed that corresponds to this? Well, if I divide both sides by m, those divide out, but then I have an m over this, oops. And then I multiply both sides by r, I get v squared is equal to gr plus fn r over m, or v is equal to the square root of gr plus fn r over m. The slower, as v goes down, eventually you'll get to the point where fn is 0. And then if v gets even smaller than that, then this just doesn't work anymore, and that's when you fall out. But if you're going faster, then you're good. You just also have some normal force that assists in supplying this centripetal acceleration. So the result of all of this is that to be safe and avoid falling out, you need speed to be greater than or equal to root gr. So in this case, that says v has to be greater than or equal to 9.8 meters per second squared times 30 meters, which is what I told you the radius was. So if I stick that in my calculator, the result I get is that v has to be greater than or equal to 17 meters per second, which works out to something like close to 40 miles an hour, which doesn't sound all that fast if you've ever driven on the freeway. But that, for a 30-meter radius turn like this, that's all the faster that you need to be going. Now, in reality, roller coasters try to be safe, so that we'll be going quite a bit faster than that, and that's why you feel pressed into your seat at the top. And in fact, if you think about it, when you sit on a chair just at rest, the normal force exactly balances gravity in that case. If you've ridden on one of these roller coasters, you feel pressed into your seat more than you normally would, which means that this normal force is now bigger than gravity, in fact, bigger than twice gravity. For you to be pressed into your seat more than you normally would, this mg, which is actually pulling you out of your seat, you would be falling out. For the normal force to feel bigger than gravity, it's going to have to be, well, it wouldn't have to be twice gravity, but it has to be bigger than gravity, because gravity is how strong it normally feels, which means that your speed is actually at least root 2, right? So this force here is going to be at least as big as this, so it'll be twice gr, but under the square root. The speed is more than root 2 above that, so that's going to make it more like 60 miles per hour, something like that. Anyway, so that's the idea with this roller coaster going upside down. You can think about that in terms of uniform circular motion. That's the second problem. In the third problem, a car is driving over a hill. See, this is the thing I was blathering about in the first problem. I knew it was coming up. The top of the hill has a radius of curvature of 22 meters. So what that means is, here's your hill, and the top of the hill is like a circle of radius 22 meters. And the car is driving over it at a constant speed, which we will call v. What's the fastest in both meters per second and miles per hour that a car can drive over the top of the hill without having its wheels leave the pavement? So again, at this moment, not here, not here, not there, but at this moment the car is very briefly in circular motion. We'll just assume it's moving at a constant speed as it goes over. And so you want to know, since it's in circular motion, it has to have a centripetal acceleration in that direction. If it doesn't have an acceleration in that direction, then the car is going to go straight out like this, right? So it has to have an acceleration to get it to curve down. So let's do a free body diagram on the car. Now I'm going to go ahead and ignore air resistance because it won't be that big. But if it is, you can put it in, but we're not going to worry about it. There is gravity. I'm going to put the normal force together of all four wheels and just treat it as one thing rather than separate, because again, we're not going to worry about torques. It's only when you worry about torques that you have to worry about, oh, is this different from this, and things like that. So we don't have to worry about that in this case. So that's all the more forces we've got. Yes, there might be static friction on wheels with the road, but that would only be if it had to offset air resistance, so we're ignoring that. So, hey, great, this isn't so bad. So now we know that the acceleration is in the downward direction. So if I sum, I'll make this x and that's y. If I say Fy is equal to May, well, the net force Fy is Fn minus mg has to equal m times Ay, which is minus v squared over r, right? Because Ay, it's in the downward direction, the negative y direction, and the magnitude has to be v squared over r. Okay, this may start to look familiar-ish, because it's related but not the same as the problem we just did. Okay, and now then the question is, what's the fastest I can go without my wheels leaving the pavement? Well, fastest, that's a speed. Let's solve this for speed, see what it gets us. So first I'm going to divide both sides by m, so I get Fn over m minus g is equal to minus v squared over r. And I'm going to multiply both sides by minus r, so that'll cancel this negative, get rid of the r there, so I'll have gr minus Fn m over r is equal to v squared, or v is equal to gr minus Fn m over r. And that's the thing that's a little different from the last problem. Okay, now, looking at this, what does it mean for the wheels to leave the road? Well, I'm going to actually write this down. Wheels touching the road means that you have some normal force, because there is a contact there. If the wheels are not touching the road, there's no normal force because there's no contact for the contact interaction, so the border between them is right when Fn shrinks, shrinks, shrinks until it just is at zero. That's right when the car is leaving the road. Okay. Fn can't ever be negative, so this will go down to zero, and eventually, all right, so when Fn goes to zero, then V is just root GR. Hey, that sounds familiar. So V is just root GR. What happens if V is bigger than root GR? Well, you can't, I mean, there's no way to make V less than root GR in this equation, but this equation doesn't apply when V gets too big. Why? Because we assumed the car was in uniform circular motion. Well, to be in uniform circular motion, right, here are the forces, divide by the m and stuff, but here's what you need. If V gets too big, you need a negative Fn to make this offset, but Fn can't be negative. So something's wrong with one of the assumptions you've made, right, because Fn can't get negative. The assumption is that it's in uniform circular motion. So if V gets too big, the car will actually zoom out here. That's kind of cool, right? The car comes driving up, and he jumps, and he lands over here, and dust flies, and here's the person he's chasing, and he has a gun, and he shoots, and I've lost control of myself. So, if it stays in uniform circular motion, when Fn goes to zero, that's when V is as big as it can be. That's when the wheels are just leaving the road. That's also, looking at this equation, the biggest V I get, consistent with my assumptions, is when Fn is zero. So the fastest he can go is root GR, which is 9.8 meters per second squared, times, what was it, 22 meters was the radius of curvature. So looking at the units, I will have meters squared per second squared under a square root. That's good. And if I stick this into my calculator, if I stick it into my calculator, I get the fastest it can go is 15 meters per second, which is, to 2 sig figs, 33 miles per hour. So if you hit a hill like this at faster than 33 miles per hour, you're going to do a little jump. If it's just a little bit faster, it's not so bad, it's kind of fun. Woo, jump. If it's a lot faster, accident city, so don't do it. Great. Anyway, that is the third problem. And the last problem, we have a spring with equilibrium length L0 and spring constant K, and it's anchored at one end. So I'm going to start by drawing this spring at rest. Now I say at the end, this whole thing is horizontal, so we're looking down on the spring. It'll be rotating around. You know it's circular because of what we're doing. And there's no friction. So when it's at rest, you have a spring here. If it's just sitting at rest and staying at rest, it'll be at equilibrium length, will be its length is L0, and then there's a mass M at the end, and then it's got a constant K. So that's what it would look like if it were at rest. The spring is rotated around the anchored end so that the block goes in circles, making one complete circle in time M. So here's the difference. It's anchored here, but it can rotate freely, and it's rotating around. So what happens then, well, I'm going to draw it over here, is the spring will be stretched as a result of this, and then this guy's going to go around and make a circle in time T. Now the radius of the circle will be, well, let's call it L. Assume the mass is small, so I don't have to worry about the extent of the mass. So the radius of the circle will be L. And then we know that it goes once around the circle in time T. And then the question is, what is L? What is the radius of the circle that it makes? Well, okay. If this guy, first of all, we don't know what this speed v is, but we'll figure it out momentarily. But knowing that he's going around in a circle, the other thing we know is that he has to have, this pen is giving me a headache. I'm going to switch to another one. He has to have, see here I am anthropomorphizing this block. It's an it, not a he. It has to have a centripetal acceleration, which is equal to v squared over L, right, the radius of the circle. So that is necessary to keep it going in the circle. What supplies that centripetal acceleration? Well, let's do a free body diagram. We're doing horizontally, so there's gravity down. I'll go ahead and draw it. And there's a normal force up. And those two are going to balance each other. And then there's going to be the spring force that way. And we know that the spring force is going to have magnitude K times L minus L0. So L is bigger than L0, so that'll give us a positive number, so that's right for the magnitude. And then that has to equal the mass of the block. So K times L minus L0, that's the net force to the left, has to equal the net acceleration to the left, has to equal M times AC, which is V squared over L. Okay, and so then the question is, what is L? Well, this already tells us what we need to do. At this point, we can just solve this for L. So I'm going to do that. I have L times L minus L0. I'm doing this foolishly. I'm not doing it that foolishly. We'll see in a moment. Is equal to, is equal to M over K V squared. But here's the problem. What is V? We don't know V. If I gave you an answer in terms of V, I would go and circle it and say not given. What is V? Well, we actually do know V. Why? Because we know how long it takes to go once around the circle. And we know how far it goes, right? Because it's the circumference of a circle is 2 pi L over capital T. So I have V squared here, and I'm going to replace it with 4 pi L squared over capital T. And now you'll see that I have been a little bit foolish in how I've been solving this. So I'll just keep going. It'll be okay. And that should have been capital T squared, and that should have been 4 pi squared, because what I did is I squared all of 2 pi L over T. So the whole thing got squared. Okay, good. So now I'm going to divide both sides by L. So that'll get rid of that squared. That'll go away. I will have L minus L naught is equal to 4 pi squared M over K capital T squared times L. What I'm after is solving for L, so I'm going to add and subtract things from both sides. I will get L times 1 minus 4 pi squared M over KT squared is equal to L naught. And what I'm going to do is do a common denominator on the left side. So I will have L times KT squared minus 4 pi squared M, all divided by KT squared. And so now I can solve for L, and I'm going to finish it up over here. L is just equal to L naught So I have to divide both sides by this is the same as multiplying both sides by the inverse of that. Kt squared divided by kt squared minus 4 pi squared m. Now I am a little bit worried about units. I want to make sure the units are fine on this. Well, okay, what are the units of k? Well, remembering that F is equal to k times delta L, forces in newtons, delta L is in meters, that tells us k has to be in newtons per meter, and newtons per meter is kilogram meters per second squared. Meter is kilograms per second squared. So this is kilograms per second squared times second squared, so that comes up in kilograms. That is also in kilograms, and then 4 pi squared is just a number, and that's in kilograms. So I have kilograms over kilograms, so this whole thing is now unitless, which is good. L has the same units as L naught. So this is our answer here. That is the radius that this thing makes. Now you might think, does this even work? Well, okay, what if t squared is too low, such that kt squared minus 4 pi squared m is less than 0? Then you have a problem. Right? Then the thing won't actually go around. But I don't think that can happen. I'll have to think harder to figure out why that can happen. I'm sure I don't think that can happen. Maybe I'll put a little yellow text up here describing why that can't happen. Maybe I won't. I don't know. We'll figure out later when I think more about it. So that is the last problem. I do want to make one additional thing. One of the problems you're going to have in the homework is going to be two masses m connected by a spring, both of them going in circles. Right? That looks harder. Now, because here's the thing, is that the center of the circles these guys are going around is going to be half of the length of the spring, right? So that's the radius of the circle, but remember the spring force is going to be just in terms of L minus L naught. So that's something that'll be a little different from this problem. But hopefully having done this problem, that'll help you figure out that problem on the homework. That's it for uniform circular motion.
हेलो दोस्तों, आपका स्वागत करता हूँ हमारे इस YouTube चैनल में। जिसको वीडियो अच्छी लगी है तो प्लीज़ लाइक कीजिए और साथ ही साथ चैनल को सब्सक्राइब कीजिए। और जिन्होंने चैनल को सब्सक्राइब कर लिया है उन्हें मैं बहुत धन्यवाद कहता हूँ मुझे सपोर्ट करने के लिए। थैंक्स फॉर वॉचिंग।